Welcome, everyone. Thank you for tuning in. I am very pleased to welcome you all to our eighth webinar in the Rain Enhancement Hub series hosted by the National Center of Meteorology and organized by the UAE Research Program for Rain Enhancement Science. My name is Sarah Al-Amri, and I am a UAE Program Officer, and I'll be moderating today's session. During the course of our last 7 webinars, we discussed the water security importance by identifying the different challenges at hand, as well as bringing in and expanding the scientific applicable solutions with a deep understanding of the issue and its solutions. Today, we will continue to expand on such solutions by presenting and discussing a third cycle UAEREP awarded project, which scientifically and operationally tackles the issue from different angles by sending autonomous uncrewed aircraft systems that assess and observing and collecting detailed real-time cloud data, which supports in identifying the best locations and times for precise cloud seeding operations. Joining me today to speak more about the autonomous uncrewed aircraft systems is Dr. Eric Frew. He's a professor in the Yan and H.J. Smead Aerospace Engineering Sciences Department at the University of Colorado Boulder. Dr. Eric Frew has received his bachelor degree in mechanical engineering from Cornell University in 1995. He received his master's and PhD in aeronautics and astronautics from Stanford University in 1996 and 2003, respectively. Dr. Frew has been designing and deploying autonomous robotic systems for over 25 years. His research efforts focus on autonomous flight of heterogeneous uncrewed aircraft systems, distributing information that's gathered by mobile robots and miniature self-deploying systems, as well as focusing on guiding and controlling uncrewed aircraft systems and complex atmospheric phenomena. Dr. Frew has successfully deployed autonomous robots in a wide variety of scenarios. He was co-leader of the team that performed the first ever sampling of a severe thunderstorm supercell, and recently deployed 2 autonomous coordinating aircrafts in a supercell. He was also co-leader of the CU Marble team that won the 3rd place in the DARPA Subterranean Challenge. He is currently the Center Director of the National Science Foundation Industry University Cooperative Research Center for Autonomous Air Mobility and Sensing. We are very honored and delighted to have him present for us today his valuable work. Audience, please go ahead and type in your questions at any time during the webinar using the chat box. We'll be sure to address your questions during the Q&A session after the presentation. Over to you now, Dr. Frew.
Thank you so much. It's great to be here. I'm excited to share our work with you. Let me get the screen started here. Great. So I'm going to present to you all some work that we've been doing on the creation of an uncrewed aircraft system to demonstrate targeted observation for cloud seedability and rain enhancement. So first, I just want to quickly acknowledge my project team. This was an international project, included work from my institution, the University of Colorado Boulder, Scripps University, Northwest University in South Africa, and Droplet Measurement Technologies. So throughout my presentation, I'll try to acknowledge where the different institutions made contributions to this project. For a little bit of motivation for our project, we are interested in performing rain enhancement. We're motivated by the fact that in order to really be efficient in conducting rain enhancement, the seeding material really needs to be applied to the right place at the right time. With piloted activities, with crewed activities, typically what happens is an aircraft will get in the environment, will look at a target cloud, and will use visual features, visual cues by the pilot to determine if cloud seeding should happen and where to go. Looking at features like the location of the cloud base, how tall the updraft might be, the morphology of the tops, the cauliflower tops there indicated, and the pilots will make decisions on whether or not they should seed the aircraft. And then based on that decision, they will go ahead and release the seeding material. Now, much of the work and the research in rain enhancement has focused on the physics of seeding, the material to do this, but effective targeting has been fairly understudied. So the focus of our project has been, how do we use in situ measurements and autonomous technologies to improve this ability to get the seeding material in the right place at the right time. So as was mentioned, we were one of the UAEREP program Cycle 3 awardees. The goal of our project was to develop and deploy teams of autonomous uncrewed aircraft systems to use real-time data from weather radar and then onboard the aircraft to measure, understand, and then target the atmospheric conditions suitable for cloud seeding. So I'll talk to you today about the progress we made in that project and some experiments we conducted at the end of our project. So kind of repeating myself here, but the goal was to develop and assess an autonomous uncrewed aircraft system. I say system here because we use multiple platforms, multiple aircraft in order to do this. I won't read through that list of technical objectives, but essentially we had to develop some analysis and modeling tools ahead of time to try to understand and predict good conditions for cloud seeding. We had to miniaturize some common instruments that are used on piloted aircraft to fit onto a small uncrewed aircraft system. One of the key aspects of this project was then developing an autonomy architecture and variety of autonomy components so that the system would make these decisions on its own with minimal human intervention. And then finally, to evaluate these autonomous technologies in an operational field campaign. The concept of operations for all of this is really four main steps or a few steps. First, we would use, and I should back up and say, all of this is intended to be autonomous. So we would get to a domain, or in the case of the original campaign that was planned in the UAE, which I'll come back to at the end, we would have been in a fixed location. So the aircraft would be in the air already, and we would use radar information, weather radar information to identify what we would refer to as a region of interest where there was possible seeding activity. The aircraft would then fly to this region of interest, find cloud base, start measuring the state of the atmosphere and identify a smaller area of interest. We would run a parcel model and some of the tools that I'll talk a little bit about here to determine if drizzle would happen or not. And then based on the outcome of those tools in situ, we would make the decision to seed or not seed. And then in our concept of operations, we had a second aircraft that would come into the domain and then would carry the seeding material. So I want to, I'll bring this up again in the future, but I want to just note that in the end of this project, we weren't actually able to release seeding material. So if I refer to an actual seeding event during our experiments, that was a virtual event where we would have released material at that location. But the concept of operations, we identify, and then we would make this determination of where to seed or not in the environment. So the first, or one of the main steps of our project was to miniaturize some of the sensors that we would need for this. So this is a picture of the sensors that we put onto our aircraft in order to do this work. There were three main sensors that we used to collect data on the atmosphere and then to make the decisions on if cloud seeding would occur or not with our material. The first is the printed optical parter spectrometer sensor, or POPS. You can see on the top there. That was a pretty much commercial product that we were able to acquire and integrate into our aircraft. That gives us, particle concentration, particle size. The next sensor to the right is the multi-angle inertial probe. That was critical for giving us the 3D velocity of the winds aloft so that we could predict if the material would be pulled into the storm and if it would be effective or not. We worked with a local company, Rain Dynamics, to build a sensor that would fit in our small unmanned aircraft sensor. At the bottom, you then see the cloud droplet probe, or CDP. That was the main sensor that required miniaturization. These are flight on piloted aircraft quite often for cloud seeding operations. And in order to get this into a size that could be integrated into a small unmanned aircraft system, we worked with droplet measurement technologies to really minimize the housing, the mass, the electronics, et cetera. Then lastly, you see in this picture a supervisory computer which pulls in all the data from these three sensors and then performs the cloud seeding, cloud seedability computations that I'll get back to in a moment. So in order to carry all this instrumentation, we needed an unmanned aircraft system or uncrewed aircraft system in order to do this. And this is really the expertise of my institution, the University of Colorado Boulder. We had been flying something called the Raven aircraft to do atmospheric science research with smaller payloads in a smaller capacity. So for this project, we worked with our vendor to build what we call the Super Raven. You can see here the picture of the aircraft and some of the statistics. It's about a 5-meter wingspan aircraft. It has a payload capacity of approximately 2 kilograms, enough to carry the different components for this mission. It has a takeoff weight of around 12 kilograms. Based on the configuration that we were flying for this experiment, it has between a 2 to 3.5 hour endurance. That's a challenging number to really articulate because it really depends on the flight profile and how the aircraft is being operated. And then for range, we're really limited by the communication that we could have. We designed this system for about a 16-kilometer communication range. The aircraft could fly further than that in the 3 hours of endurance, but we had to maintain communication with that aircraft at all times. And so you can see here just the pictures, the middle picture, you can see the cloud droplet probe on top. That was another challenge here, is getting this thing balanced in order to carry all of the equipment. Here I'll show a quick video of the aircraft just so you can get a sense for the scale and the size. We actually do use that table and then a bungee cord to launch the aircraft. It's an efficient way, or it's an effective way to be mobile. We can take a table and the bungee anywhere we need to go out into the field. We can stake out the bungee in a few minutes, and then we can take off on this ramp. And so you can see here a sense of scale and see the aircraft in action. So the next main component of our system is the dispersed autonomy architecture. I call it a dispersed architecture as opposed to a distributed architecture, just to really indicate the scales in which these components are spread out around the world, quite frankly. So you can see here the architecture. I'll go through the components here in a moment, but I really want to stress that there are 3 different levels, if you will, of where the autonomy architecture lives. To the far right, you can see on board the aircraft. For the experiments that I'll describe shortly, this was flying in the US Great Plains. On board the aircraft, the key piece of autonomy is this cloud seatability algorithm that I'll talk to. So we're making decisions with our sensors on board the aircraft in the environment to assess the conditions of the environment in situ. So that runs on board because that's where all the data is located. Next, you can see this sort of middle area at the field site. So this is the ground command station. We ran most of the autonomous decision-making there, in part because we had computers that were much stronger and faster than what we could put on the aircraft. Because of aviation regulations, we would always have a communication link to the aircraft, and we determined that it was much more efficient to send flight plans over this communication link to the aircraft rather than trying to send models and radar data up to the aircraft for the decision making. So really the key decision making happened at this field site. There are 2 major components that we had to create for this project. One is this targeted observation and seeding finite state machine. A lot of the coordination occurred there, which I'll talk to in a moment. And then this path planning algorithm to search the region of interest to identify these areas of interest. So that would happen at the ground station, which would potentially be up to 10 miles away from the aircraft. And it would determine how the aircraft should fly and would give the commands to the aircraft on board to follow. And lastly, to the far left, we used, I sometimes joke, we did cloud computing in the clouds, but we worked with our colleagues, as I mentioned, at Northwest University. They would use feeds of the weather radar data from the Great Plains, and they would run an algorithm called the Rapid Evaluation of Convective Cell Environments for Seeding, or RECIs, to make predictions on where the storm motion was moving and where potential cloud seeding conditions would occur. And it would send that information through the public internet to our field site for further coordination. We also built out some observation GUIs that our colleagues at the NCM were able to follow our experiments, and then potentially other operators, scientists, or users could interface with the system from anywhere in the world. And just as the very far left, again, we were pulling data from the US NextRad radar in situ, while we were in the field to make the decisions on where to go and how to operate. And so this dispersed autonomy architecture is what really pulls together all the different components from our teammates and allows the system to operate fully autonomously. So once the aircraft are launched, this architecture requires no human intervention. Now, you'll see shortly we had the opportunity for human operators, human pilots, human users to engage with our aircraft, and we had occasions where our operators would interject. But the intention here is that this entire operation, once the aircraft are launched, can operate autonomously, and our human operators are just, as we say, on the loop, making sure things are operating smoothly. So some of the key components of this system, first, kind of working a little bit right to left on that previous picture, was the RECI's algorithm. So this is an approach, or this is an algorithm using the weather radar data to make predictions on how the storms would be moving, how the clouds, I should say, would be moving, and feeding information to the team in the field. So this is just one short animation of some example data. You can see clouds and convection forming. We're using computer vision techniques here to identify these clouds and make predictions on how they're moving, and looking at some of the reflectivity data to try to approximate and predict the strength of the clouds initially. We didn't demonstrate fully the capability of this to assimilate the location of the aircraft and the time to reach these different storms into the decision making. The intention here is, as you can see in this video, perhaps multiple storm cells or clouds might evolve together, and so there's a decision to be made of which one to go to. We can incorporate understanding of where the aircraft is located and do some initial balancing of longevity of predictions for the clouds and the aircraft location and time to get to the aircraft. For the flight experiments that I'll show shortly, really there's only one nearby storm at a time, but we can make some predictions there. And then on the far right of this slide, we have this XML schema that we use to communicate with our path planner to condense these polygons of the storms into a form that are easily shared across the internet into, in our case, the ground station in the US Great Plains. I alluded to the finite state machine. This is really just a set of different, we'll call them modes or types of behaviors that the aircraft could be in. And depending on where we are in our mission, we are in different modes, and you can see how different modes can transition into other types of activities. I won't go through the entire diagram here. You can see in sort of the middle bottom, the search for seedable region. That was really the main node here. The aircraft is in one of the regions of interest that has been provided by that RECI's algorithm. It's performing a search, and then depending on what's measured on board or not, we'll transition into the seeding mode there, or the seeding evaluation mode. We had two different versions of this. One, if we were conducting the full mission with just a single aircraft, meaning the sensing aircraft was also the seeding aircraft. And then the main ConOps that we were building to is a separate sensing aircraft and seeding aircraft. So in the case where there's two aircraft, the seeding behavior would really be a call to a second aircraft to come into the environment, and then the first aircraft would trail behind it to create this evaluation maneuver to try to sense the impact of the cloud seeding. And so this type of picture shows you how we're coordinating those activities. Part of the work was also building out these path planning routines in order to sense the region of interest. We had a variety of different paths that we could pick from, sort of your traditional raster scan or lawnmower pattern, different spirals, or just a straight diagonal through the environment. Had we had more time, we were interested in trying to do some tests on which of these patterns would be most efficient and effective. We used the raster pattern most of the time because it was fairly straightforward to set up the pattern and align it with the regions of interest that we had. We do account for the storm motion, and so these patterns are actually followed in a storm relative, I say storm, in a cloud relative frame of reference, so that region of interest where there's potential seedability is likely to move, and so we can actually scan that region as it moves with the clouds. So the cloud seedability algorithm is a key aspect of what we were running on board the aircraft. Essentially, we did a lot of data processing offline. So we looked at data from some of our colleagues, and we ran some models offline looking at essentially CCN concentration and updraft velocity, and did some predictions on when seeding would occur or not. On when drizzle would occur with or without seeding, and if the presence of seeding material increased the time for drizzle to occur, we would consider that good cloud seeding conditions. Now, we did this through a variety of different conditions with some uncertainties added into the mix, and so what we ended up with, you can see on the bottom here, are these essentially these maps of when the probability of seeding would occur would be high or low based on the CCN concentration and the updraft velocity. Those maps were something that were fairly easy to put into a form that could be carried on board the small computers on the aircraft. And so the goal here was to take these offline calculations and condense them into a form that could be run online. So we would have this map essentially of probability based on CCN and updraft velocity. We had a variety of these different maps parameterized by the LCL temperature, essentially the temperature at the cloud base. And then depending on the conditions that we were in, we can go into this map that was pre-computed, and we could use this to then make some decisions on if cloud seeding was likely to improve or not. Essentially, I believe we used a 50% probability. Maybe we used the 75% probably for some of our experiments as the threshold, and something that was pretty easily encodable in the aircraft. We did create a dashboard for this so we can observe some of these things happening online. This wasn't something that we really incorporated too much into the flight test that I'll share next, but if a user or an operator was participating with this system, they could look at this dashboard and they could see some of this information coming. I'll just note in the middle of this, you can see some of those circle icons. Those indicated times when an aircraft would be in good conditions, and you could even see kind of here this dashboard indicates when we would command start and stop seeding in some of these things. And so this is something that the scientist user could use to track what was going on in the storm environment, in the cloud environment. We also built out an interface for the pilot of the aircraft to maintain an awareness of the aircraft. Here, I mentioned there is an operator that could intercede, and so you're seeing some parameters being set by the operator. The LCL temperature was often set before launch. The operator had the opportunity or the ability to transition between modes. If we wanted to just go directly to a seeding maneuver or some other elements, we could command those. We could command the type of paths that we wanted to create, etc. But all of these things could also happen autonomously with the operator, just maintaining an awareness of what was going on with the aircraft. And you can just see here, this is a simulation of the aircraft following these patterns that we created. So I want to talk about our field campaign. So unfortunately, due to the global pandemic and some other factors, we were not able to make it to the UAE for the original campaign that we had planned in the Fujairah area. So instead, we conducted a campaign in the US Great Plains. You can see here a reference. That's actually, it says under review, but that's been published just recently that summarizes these results. So we spent 3 weeks in the US Great Plains doing a campaign. So here's just a few photos and some video clips of this work. I mentioned before that we did virtual seeding. So in this field campaign, we were not able to actually carry seeding material. We developed an aircraft to carry material, but we were not able to fully verify that and get the full set of approvals to release material for this campaign. So we still, however, conducted operations with 2 aircraft. I alluded to this earlier. There's the sensing aircraft and the seeding aircraft. The lower right video shows the sensing aircraft. You can see the MIPS multi-inertial probe out the front. That's the long probe sticking out the very nose here that measures the 3D velocity. It's a of the winds. It's a multi-hull probe. You can also see the cloud droplet probe on the top of that aircraft. In the top right video, you can see a view of the sensing aircraft from a different aircraft that's trailing it. So that's the same aircraft, the Super Raven. The bottom left video of 2 aircraft shows you the Super Raven aircraft from it shows you the our second aircraft, what we called the seeding aircraft. So for this work, we just used our Raven to emulate that performance. And so that lower left image from an aircraft shows you the coordinated movements that were happening. I mentioned in the few slides back that the sensing aircraft takes an evaluation maneuver, essentially trails behind the seeding aircraft so that it could potentially sense the impact of what's happening. So you can see in that video, we captured some results from those maneuvers there. And so finally, on the far left, you see the radar picture. So a lot of this campaign was spent in what we called a mobile nomadic operations. We would actually each morning look at the weather, try to predict where there would be good conditions, and then we would move to that spot in order to be in good conditions. And you can see here one of our successful days where we were able to position ourselves in front of these clouds that were moving towards us so that we could put all of the autonomy to the test in an actual realistic environment. In the Fujairah campaign that we weren't able to conduct, we would have had a fixed ground station, and we would have waited for the clouds to come to us, but that wasn't something we were able to do in the large expanse of the U.S. Great Plains. So over the course of these 3 weeks, we created a series of what we call technical capability levels, so we could demonstrate all of the different autonomy components in the environment. We flew 9 flights, where a flight was really a takeoff and landing of the aircraft, and we were able to conduct multiple missions in the course of several flights. Over 3 weeks, we were able to fly 9 flights, so not every day were we able to actually position ourselves in front of the clouds that were effective, and we were able to culminate in 4 flights demonstrating the full capabilities of our system, meaning 2 aircraft fully coordinating based on the radar data that they got from the Recce's algorithm running at Northwest University in South Africa, communicating to our ground station, communicating to the aircraft, fully coordinating the aircraft operations. So we were very excited to be able to demonstrate those autonomy components at the conclusion of this project. The map just shows the different locations where we flew. It's a little bit hard for scale. Sort of from the left side to the right side, gosh, I'm not sure how many kilometers is, but that's 6 hours of driving cars to get back and forth. And so you can just get a sense of scale for the campaign that we conducted there. So again, we culminated in being able to demonstrate all of the autonomy pieces working together as we had designed them. Through this, we learned a few things, and so which lessons learned and recommendations for future work. I fully acknowledge that we were not able to demonstrate this technology in the United Arab Emirates because of, as I said, the pandemic and then some further issues, mostly related to the approvals that were necessary from our end to get there. So the next step would be to love to be able to assess this technology in the UAE. One major difference potentially is going to be the hot temperatures of the environment there compared to the temperatures in the U.S. Great Plains, and understanding the impact on the aircraft and the flight performance itself. The communication environment is also critical. So we were able to always have good communication with the internet, and so that's pretty critical for the success of the ConOps that we had, the architecture that we developed. The other thing that I want to note, we did not, as I said, actually release cloud seeding material. Even if we had, we don't think it would have been on a scale to measure substantial impact on the atmosphere. And so future work could be done to really craft a larger scale experiment to assess the mission, assess the ability of the aircraft that we in the autonomy to get the cloud seeding material in the right place. We judged this mission by the autonomy technology working and assessing the environments against the algorithms and against the predictions that we had, but we would need an entire order of magnitude larger experiment to really assess the actual system and the seeding material release on the environment. And so that's something that would be important for future work or future assessment of this type of a system. The sensor in the aircraft, as I mentioned, I didn't mention this explicitly, we were focusing on aircraft that a team of 2 people could operate. And so that meant the seeding aircraft was limited in how much material it could cover. Moving forward, it would be appropriate to build a much larger aircraft to carry more seeding material. Because of the way we structured our project, because we had a sensing aircraft and a seeding aircraft that weren't the same, you could envision swarming or flocking concepts with multiple aircraft doing sensing and multiple aircraft doing seeding, and providing for a lot more information on the environment. This also leads to cooperative mapping concepts. We had a single aircraft, and so the understanding of the environment, we really didn't do any mapping. We looked for local in situ conditions, and then would have made instantaneous seeding decisions. But with more aircraft, you can create a map and perhaps have more opportunities on where to seed or not seed the environment. And also there's opportunities for more machine learning algorithms to do more advanced data science and data processing on the in situ measurements before making those decisions. From the autonomy architecture perspective, there are a variety of things that could be done. With our connection back to the internet, you can think about doing data assimilation in real time. So actually taking our measurements, feeding them back into to numerical weather prediction models, say back at NCM, and trying to make predictions online on where to go. That wasn't something we were able to do in this project. We'd love to see more explicit formation control, so multiple aircraft in formation could get more information on, say, updraft velocities, the distribution of the cloud particle CCN, some of those things. And then lastly, there's opportunity for informative path planning. And so I mentioned that we did these raster paths or these spiral paths. These were really assuming that the chances of good cloud seeding conditions were somewhat uniform across the region of interest, but statistical techniques could perhaps allow us to make even more informative decisions on where we go in order to hone in on particular areas of cloud seedability within the region of interest if we have a little bit more understanding about the probabilistic distribution of where things might go. And then lastly, something that is challenging to talk about because it really is a function of a lot of the ongoing aviation regulations. But in order to do this work in an operational setting, you would want your drones to fly beyond visual line of sight, meaning out of eyesight of the operator. The work that we did in the US Great Plains, we always had to keep the aircraft within a mile of our ground station so that we could see the aircraft and do collision avoidance with other aircraft. The aviation authorities across the world are working on rules and regulations to allow this beyond visual. It requires integration of transponder technology into your drones and other things. And it's something that will really be necessary in the future. And so this is a combination of technology and regulation moving forward. We had anticipated cooperation from the Fujairah and Dubai aviation authorities to be allowed to do beyond visual line of sight for this project. So that was something that we had thought we could perform. And just again, one of the things that we were not able to achieve with our project was getting into this full beyond visual line of sight capability. That's one of the major reasons why we stayed in the US to do the flight campaign that we had done. So that ends my presentation, and I am excited to take questions. Thank you.
Thank you very much, Dr. Frew, for the insightful and the very informative presentation. We have a few questions to address during our Q&A session over the next 15 minutes or so. The first question, as a UAEREP third cycle awardee, what are the improvements, as in additions or subtractions, you'd like to see in the future when it comes to UAVs?
Great question. I think I'll be frank and say the biggest struggle my team had was understanding the aviation regulations in the UAE. And I alluded to this a little bit during my presentation. We struggle to fully understand the process and to reconcile the rules and regulations of our home institution with what was needed to gain the full set of approvals to operate in the United Arab Emirates. And so my first recommendation would be for an international team such as mine to really stress the challenge there and to see if there are ways to start working some of those approvals very early on in the process, perhaps even before an award is made. That would have been valuable for us. Now, going into this project, we had acknowledged that this was part of what we were trying to understand. And so I didn't talk really a lot about that. I didn't want to focus on that side of things. So that would be my first thought, is to just, a little bit more clarity on the part of or making sure the person who's going to do the work understands the challenge there. And that's true everywhere. We had challenges with the US regulations for some of these things. I also mentioned that the cloud seeding release was something that we didn't fully understand all those approvals, even back home. The other element to this, which I think is important, is communication and understanding the communication environment. How would a team be able to operate, mobile radios, mobile equipment in the mountains of Fujairah? Is the radio technology, is the mobile broadband good enough to be connected to the internet? An understanding of those issues would be important for any team planning to fly UAS like we did in the UAE. I think that's very surmountable, but we just didn't have a full understanding ahead of time of what that would look like.
Thank you, Dr. Frew. Our second question, Would you consider three as the ideal number of UAVs in the fleet, or would you recommend adding more UAVs to the fleet to improve the rain enhancement process?
Yeah, so I think implicit in your question is the fact that our team built 3 aircraft for our project. We, as I described, flew 2 aircraft. The original concept of operations was actually a team of 2, a sensing aircraft and a seeding aircraft. We were focusing on what we call small UAS. There's some debate on what the definition means, but in my view, that's in some ways an aircraft that a team of 2 people can operate. And so that really drove a lot of the design decisions for us as something that was very easy to operate, easy to take into the mountains, take into the US Great Plains to operate. And so building a system of 2 aircraft, we wanted a single spare aircraft. So that's why we built 3 aircraft. We were also, frankly, limited a little bit by the budget of the award of this program. And so that limited us to 3. So that's a very long-winded way of getting to my answer, which is 2 or 3 is not the ideal number. That was really the number that we could realistically manage with the team that we had, given the constraints that we were operating in. It is a challenge from a logistical perspective to manage multiple drones and get them all to operate. And so I would feel challenged to try to fly 3 or 4 at the same time. But I think you can't sample enough of the atmosphere, meaning if you could fly 100 of them, you'd want to fly 100 of them. So really the ideal number is as many as you could kind of realistically operate with your team in this environment. 3 or 4 gives a nice, if you could fly 3 or 4 in a formation, you get a nice understanding of a lot of the gradients and fluxes in the environment. So I'd say maybe an ideal formation of 4 would be something to strive for, and then more if you can.
Thank you so much. Our third question asks, what parameters determine the most efficient path pattern? For example, how would the operator determine the raster path pattern is more efficient than a spiral pattern?
Yeah, great question. And I alluded to this a little bit in the presentation. I'll say we focused on the raster patterns in large part because they were easy to understand and easy to create given a polygon region of interest of some unknown shape that you're going to get ahead of time. The main parameter that we actually had to account for in creating those patterns was the wind direction. You'd like to align those scans either with the wind or against the wind, so the aircraft itself is flying in an efficient configuration. If you're flying kind of across the wind, it's not as fuel efficient for the aircraft. The raster pattern really assumes that the area you're searching has sort of uniform likelihood of what you're looking for. There's no part of the area that is or isn't better to go to first. So the next step in these informative plans would be some sense of prior probabilistic distribution of where you'd like to be in the environment. And so we would identify these polygon regions of interest from the Recce's algorithm, but then that was all we kind of had to go to search for. If you had a probabilistic model that perhaps indicated that the center of this polygon was more likely to have seeding material, you might do a spiral behavior where you start on the inside and spiral out. So you study the more likely spots first. And then vice versa, if you really think the edges are important, you might spiral in. So some tool to provide a probabilistic assessment of where the conditions might be best would help us be more informative on these patterns and might help us, choose behind the examples that I gave, or even create, more unusual looking shapes that incorporate these prior understandings of what you might be looking for.
Thank you so much for that, Dr. Frew. Our fifth question asks, what safety measures could address UAVs causing potential property and personal damage?
Yeah, that's a challenging question. When it comes to property, so I guess, inherent in that specific question is this assumption that at some point this aircraft might fall out of the sky, right? If we're talking about property damage, safety of people on the ground, we're assuming that something's going to go wrong, something will happen to the aircraft. These days, commercial systems can come with redundant sensors and redundant systems. So you can have multiple versions of a lot of the flight critical sensors on the aircraft. If you design your fixed wing aircraft, you can design it so that the actuators, the servos, have multiple versions. So if one of your actuators fails, that you still have control authority to fly the aircraft. One of the reasons why I like flying the fixed wing aircraft, I didn't call this out specifically, but when people talk drones, they often talk these multi-rotor aircraft that can take off vertically, which is really nice. But if a motor fails on one of those things, it quickly tumbles out of the sky, whereas a conventional aircraft or a fixed wing aircraft can glide to safety if something goes wrong. And so there's already an inherent safety feature built into the aircraft that we fly, in that if something goes wrong, they don't just immediately become a brick, as I like to tell my students. They still will glide safely. So that also helps. In the aviation world, the big concern is typically other aircraft. In fact, it's less about what happens on the ground. The sense is that there's usually a lot of open space on the ground that one can find. But because you're flying in airspace and it's hard to see other aircraft, that's the big fear. So when I alluded to BV loss before, the major safety threat is the drone getting in the way of other aircraft. The operations that we wanted to conduct start to get close to where commercial airlines might fly, and some of the flight paths into Dubai Airport, for example, fly over the Fujairah Mountains where we may have operated. And so the piloting community worries a lot more about getting in the way of other aircraft, and transponders and radio communication are the key technologies for doing that. I also say we fly the smaller aircraft in some ways because the small size means they don't have the kinetic energy that larger systems have. So if that aircraft that I operated, it's made of foam, in fact, and so it's fairly soft compared to a lot of other aircraft it were to impact things. And so the design itself also has some inherent safety properties with it.
Thank you so much for the amazing answer.
Mm-hmm.
Our last question asks, what do you think about expanding the utility of UAVs for weather monitoring purposes aside from rain enhancement?
Yeah. So sorry, you said for weather modification or for just studying the weather?
For what weather monitoring purposes? So
monitoring. Okay.
random data collecting for further studies.
Yeah. So I didn't talk too much about this in the beginning, but really my group came to the rain enhancement application through other work and other types of weather monitoring applications. Not to talk too much about other projects of ours, but we use these same type of drones to study severe storms here in the US, tornado formation, for example. And so I actually was in a campaign this May and June doing some of that work. And so I think there are absolutely a lot of applications, a lot of uses for this type of technology for a lot of different weather monitoring applications. As I mentioned, we look at severe storms here in the US. The initiation of convection is another application. You could easily envision using our drones, the system that I just described today, not only to want to study the clouds and seedability of them, but what about the conditions leading to the formation of clouds in the first place? If we're sampling the environment ahead of time, we can measure updrafts, we can measure temperatures, we can measure the humidity prior to even the formation of something that shows up on the radar. And so I think there's a lot of application there. As I said, the sky is very large. So the more aircraft you can fly, if you want to call it a swarm or a team, whatever you want to call it, the better. If we can get fluxes, if we can get gradients of information, that would be fantastic. I know there is work by colleagues and others looking at other kinds of sensors as well. You can measure radiation fluxes to try to understand the heat transfer that's impacting the environment. We could measure the humidity. In fact, we do measure the humidity for this. You can start to think about carrying LiDAR to get other measurements of the wind, et cetera. So there's a lot, pretty much anything that you want to understand in the atmosphere. I think there's applications for this type of drone technology to help do that mission. And from my perspective, I'll just conclude by saying, the key thing that a drone gives you is measurements in the atmosphere. We understand a lot from radar, but there are certain things that you can't get without being in the environment. And so that's what the drones bring you.
That's a great conclusion, Dr. Frew. Thank you so much for presenting your innovative and UAE REP third cycle awarded project for us today. You covered the reasons why UAVs are great to be included in the rain enhancement scenario. You discussed the functionality theoretically, scientifically, and operationally in detail, as well as their structure and components. You wonderfully explained the different aspects and stages needed to go through their operation, as well as displayed their successful flight. You also discussed the challenges and opportunities the UAVs could provide for for a region like ours. We are very much looking forward to utilizing the UAVs in the UAE to enhance the rainfall soon. Thank you so much for presenting your insightful work today, Dr. Frew, and our eighth session of Rain Enhancement Hub webinar series. It's been a great honor and pleasure.
Thank you.
Thank you. The webinar is recorded and will be available on our website for those who missed the live stream. I encourage you all to attend our next webinar, which we'll advertise on our channels in the near future. Thank you very much for everyone who tuned in, and I wish you all a great rest of your day.